So, we have seen through the last few lectures that we have these downsampling and upsampling operations followed by filters, right. I mean there are equivalences, etc. So, in the downsampling process we are reducing the sampling rate, in the upsampling process we are inserting zeros, right. So, we may upsample and then we may pass them through filters towards the purposes of interpolation. One of the questions that you may ask is, am I not wasting my computations because I have a lot of these zeros that I am inserting because of the upsampling process, and when I am filtering I am basically filtering these zeros, right. My computation is basically wasted by filtering these zeros. Can I do something efficient towards this purpose? And this problem was an issue way back in the Bell Labs when people were investigating into multi-rate filters, essentially towards adjustable multi-level filters, or in possible applications of TDM FDM conversions, etc., where they have to deal with these adjustable sampling operations followed by filters. And you have these situations where you have these huge filters and you want to basically filter zeros through such filters. It is a computational burden, has huge latencies, right. You suffer on the throughput, it introduces latencies. Now it is basically not efficient. So, fortunately a researcher thought about these problems and that was Morris Belanger and his team in 1976. So, the idea in polyphase representation is create a set of lower order filters that work efficiently under multi-rate operations. Okay, and this idea also leads us towards simplified theoretical results and has a lot of very interesting consequences for designing efficient architectures for multi-rate systems. So, let us start with a basic idea. So, this is the original idea is to create a set of lower order filters that work efficiently under multi-rate operations. So, let us start with a basic idea, I mean an example I would say. Now, we have h of z is basically the z transform of h of n. So, if h of n are my filter coefficients, right, in the transform domain I can write it in this form. This is no big deal, but what is interesting is we will follow the divide and conquer approach that is often seen in computer science, right. We separate h of z into even and odd coefficients. So, we do this, then h of z can be written as follows. We have a summa n equals minus infinity to plus infinity h of 2n z power minus 2n. So, at all even points I am getting this, I am grouping all these terms of this filter, and then I group all the odd odd parts in this form. I just wrote it as z power minus 2n here. This is basically h of n z power minus 2n plus h of 2n plus 1 z power minus 2n plus 1, that the additional factor z power minus 1 I just pulled it outside here, right. So now let us see how this is important. So if we let E naught of z to be h of 2n z power minus n and E1 of z to be h of 2n plus 1 z power minus 1. If I let these two filters like this, then my h of z can be written as E naught of z square plus z power minus 1 E1 of z square. Right, it is pretty straightforward. You do not touch this h of 2n or h of 2n plus 1, instead z is replaced by z square. So now what is happening here, we have decomposed the original filter into two sub filters that are potentially, that could be potentially of lower order, right. So we will see this with an example. To make it more clear, say suppose h of z is 1 plus 2 z power minus 1 plus 3 z power minus 2 plus 4 z power minus 3, right. You first group the terms. This is one part, the other part is 2 z power minus 1 plus 4 z power minus 3, right, and my E naught of z is basically 1 plus 3 z power minus 1, and my E1 of z, pull the z power minus 1 outside, is 2 plus 4 z power minus 1, right. E1 of z square will be 2 plus 4 z power minus 2 and z power minus 1 times E1 of z square will give you this, and then E naught of z square will give you this, right. Just to give you, from here I can go to E naught of z square will give me this. To get this, I have z power minus 1 times E1 of z square. Now the aim, at least the goal, is if I now use lower order filters somehow instead of this higher order filter, and somehow use lower order filters in parallel to do certain operations, maybe I am cutting down my time in my filtering process, right. If I have to filter, take a signal and filter it through this filter h of z, I have a latency because I have to go through the delay of this filter, so I incur latency. But instead of that, I cut down this into two sub filters of lower orders and maybe let them work in parallel and somehow combine the outputs from each of the filters in parallel, can I improve my computational efficiency. So we now have an idea here, right. Like even in CS, for sometimes it may be in computer science, you may see the scenarios where you may divide and conquer, right. You have a computation problem, you just separate them into even parts and odd parts or some two parts, depending upon what your constraints are, and then you do the computation, you carry the computation separately on each of the parts, right. So the same idea is sort of extended in some sense to the filtering operations, and we will see how this polyphase, this is basically a two phase representation. So we looked into the case of FIR. We can think about the case, this is the FIR case, finite impulse response. We can think about the scenario for the IIR case as well. So this is case A. And this is case B, which is the IIR case. So suppose I have h of z to be the simple first order IIR low pass filter. I can write this in this form. This is saying that this is a plus b divided by a square minus b square, nothing more, right. It is very simple to see this structure. Now my E naught of z is 1 upon 1 minus alpha square z power minus 1, and E1 of z is basically alpha upon 1 minus alpha square z power minus 1. Right, these are two sub filters in the same form. Basically, if I wanted to go back from here, I could get to this step with E naught z square, and from this I could go to this step via z power minus 1 E1 z square. Right. We looked at both the cases for the FIR as well as for the IIR case. Now we would like to extend this idea we would like to extend this idea for any integer m. So let us see the generalization. Now I can write h of z as summation n equals minus infinity to plus infinity h of n times m z power minus n times m. So basically I look at modulo m components, right. I just basically have a delay followed by this dot 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 plus with m minus 1 delays I have right. Instead of just grouping into even and odd for the case of for the case of split of 2, if we can split by 3 we take modulo 3, right. all those with modulo 0, modulo 1, modulo 2, and we grep those filter coefficients, and then we regroup the filter as follows, right. And this can be compactly written h of z is sum L equals 0 to m minus 1 some delay z power minus L times e suffix L z power m, and this is basically type 1 polyphase. And the term polyphase indicates multiple phases. If it is just a 2-phase system, it is even odd, 3-phase 0 1 2, 4-phase 0 1 2 3, so on, right. M phase 0 1 2 so on till m minus 1. So this whole this function this filter h of z can be written in this form very compactly. Basically we are folding the delay also, and then this is a unit delay followed by some filter, so on with an m minus 1 delay followed with this filter. So the z power minus m of a basic filter, which is EL of Zm, is where we can write, where EL of Z we will link it with the impulse response of the filter, which is, so EL of Z is given by this quantity EL of n z power minus n, and EL of n for the nth phase is basically h of nm plus L, where L is between 0 and m minus 1. This is pretty straightforward, right. EL, we start with this EL, which is our, this is nm plus L. L equals 0, we have this. L equals 1, we have this. L equals m minus 1, we have this, right. And then this is our EL of n. Our EL of Z is basically the Z transform of EL of n, and everything just falls in a straightforward way. So now this gives us an idea that given any arbitrary filter, we can do an M polyphase representation of the filter. That means we take the filter, we decompose it into sub filters of lower order, which will be connected through a delay line, right. The original filter is connected to all the sub filters via a delay line. Now one of the exercises or homework exercises is show that there is an alternative representation to this filter, which is termed as type 2 polyphase, given by this representation, where you look at the permutations of the filters EL of Z, and then you connect them to the original filter, and this representation is basically called type 2 polyphase. Type 2 polyphase representation. And I remark that we need both of these two representations when we discuss how we want to bring in efficient architecture. Sometimes you want type 1 representation, sometimes you may want type 2 representation to simplify your architecture. So therefore you need to know both of these representations, and this is nothing really fantastic here, but it is just basically if you look into the permutations of EL of Z, you can simplify the transfer function, right. Just follow this definition and convince yourself that H of Z can be written in this form in an alternative way. The proof is pretty straightforward, it is very simple exercise. So I think with the above tools in mind, I mean we have a very powerful tool now, this is which is polyphase representation. So the concept is take a long filter that you have, right, and then chunk it into sub filters, and each of these sub filters are connected via a delay line and some operation to get back to your original filter. We saw that, right. H of Z is basically E naught of Z square plus Z power minus 1 E1 of Z square. Similarly for modulo 3 split, we can have a Z cube term there, right, E naught of Z cube E1 of Z cube E2 of Z cube, and combining elements would be the delay elements, right. So we can think about an architecture which is very similar to that, and these architectures are very efficient, we will realize when we have to do multi-rate operations, whether we have to filter first or filter later on. It will cut down the latencies because we are dealing with lower order filters, provided we are operating in parallel we can cut down the latencies, and second we will see how we can do efficient computation by not filtering these zeros, because if we take these zeros and we filter through an interpolator, I mean it takes quite a lot of time, right, and we can save some of those cycles by doing filtering operations efficiently.